Hi everyone, welcome to lesson 19. Today we're talking about projections and projection matrices, and this is information that you are familiar with if you've taken Math 243 and actually been introduced to what dot products are. I'll review all of that because I know that 243 is not a prerequisite for this course, but you will see once you understand what the dot product is how it is really directly related to projections. So let's start here, section 4.2, that's today's section. We're on page 151. I'm not going to walk through the details of the summary here other than to say we'll talk about these dot products right here. The error vector is easily defined, and I'll show you several examples of that. And then the projection of B onto some subspace. So we've thought about projections as a vector onto a line, onto a one-dimensional subspace, but we can of course project onto any dimension subspace. And then there's the projection matrix here, which is really directly related to the dot products, and I'll show you how that works. To begin, Strang provides an excellent example of two different projections for the vector 2, 3, 4. So what you want to do is make sure that you read through his example here and understand everything that he's talking about. It's very important. And I'll just point out for you the vector that he's doing the projections for is the vector 2, 3, 4. So all of that is for you to read. What I want to do is point out a little bit in the terminology. So we have orthogonal complements again. That's a review from section 4.1. Understanding that in this case he's talking about a plane in R3 and a line in R3, and these two things are orthogonal complements, and he relates that back to the projections. As you continue reading through, you'll see that he references this whole concept, right? He says, this is perfect. The goal is reached, right here. This is perfect. Our goal is reached for this particular example. We have the same goal for any line in any plane in any n-dimensional subspace in m dimensions. And it's not just a line. What he's talking about here is the ability to project onto a subspace and look at the error vector and realize that that error is orthogonal to the subspace that we projected onto. And then similar to what we talked about before, he's going to be looking at the vector, not necessarily x in this case, but just to review back where we had the R component, which was from the row space, and then we had the null space component. So because the row space and the null space for A are orthogonal complements, we know that we can break down the vector x in this manner. And it's a similar type of situation here. So he goes on to talk about how we do the projections, and we'll talk about that, but this is a very important statement here. Every subspace of Rm has its own projection matrix. We have a means of projecting onto that subspace. And then he continues with the best description of a subspace is a basis. And if we take the basis and we put those vectors in as columns for a matrix, then we're projecting onto the columns of A. And projecting onto the columns of a matrix is going to allow us to address several different items, one of which he's talking about here, but then also when we get into section 4.3 and we start talking about solving the least squares problem, it'll be exactly the same concept. So this is one of the obviously powerful applications of linear algebra, is our ability to take vectors, put them into a matrix, and do operations on that matrix. All right, so I'm leaving you to read through that example. What I want to do now is talk about projection. He talks about projection onto a line. What I really want to do is start out just by letting you know, for those of you who did not take Math 243, what the dot product is really calculating. So the dot product is really the length of the projection. So in this case, think about the gray vector. We are projecting the gray vector, which he calls the B vector, onto the A vector, which is the blue vector. The resulting projected vector P is the black vector, and the error vector, which he refers to as E, is the red vector. And that's my color coding, and I'll be using that throughout today's conversation. But what's important for you to realize is that the dot product is the length of this projection multiplied times the length of the vector that we have projected onto. Let's take a look at what that is. You remember A dotted with B is equal to the magnitude of A multiplied times the magnitude of B times the cosine of the angle between them, and remember that angle is right here. So it's easy for us to see, and it's critically important to understand that this is the length of the projection from B onto A. And so we can actually solve for this, and we end up with the length of the projection is equal to the dot product, A dotted with B, divided by the magnitude of A. That gives us the length of that projection. Now, to actually build the projection, the vector P, we are going to take the length of P and we're going to multiply it times the unit vector in the direction that we're going. Well, we know what direction we're going. We have a direction in the same direction as A. And so what we want to do here is multiply by A hat, which is equal to really the length of P. It's the A vector divided by the magnitude of the A vector. Now what I'm going to do is just show you a couple of steps of algebra about how we can rewrite this. This P vector then is equal to, and I'm going to come back in and substitute this item here. It's really A dotted with B divided by the magnitude of A times the A vector, and that's not our dot product, that's multiplication there, divided by the length of A. And so what we have in the denominator is really the length of A squared. So this projection vector, the vector P, is equal to A dot B divided by the magnitude of A squared times the A vector. Again, for those of you who took vector calculus, this may look familiar to you, understanding what these pieces are. But now that we understand about inner products, how dot products and inner products are the same thing, we can rewrite this. The P vector, the projected vector, is actually equal to the A vector transpose times the B vector, that's the dot product of A and B, divided by the A vector transpose with itself, multiplied times the A vector. And for the denominator there, remember, the magnitude of A squared is equal to the A vector dotted with itself. And now we're just writing that as the A vector transpose times A. So this is giving us, through dot products, what that projection vector is. Let me just highlight here, come back up a little bit. In this situation, the dot product is a negative number. That happens when our projection, remember it's the length of this projection times the length of the vector that we are projecting onto. And in the case where we're negative is when those vectors are pointing in opposite directions. So in this first example, P and A were pointed in the same direction, but when we say projecting onto a vector, we really mean projecting onto the line that contains that vector. Let me talk just a little bit about something that Strang talks about here. We're going to call the projection vector, it's obviously some scalar multiple of A. the vector that we're projecting onto. Could be negative because it could point in the opposite direction. He calls it x hat. We've already reserved x hat to be something else. So what I'm going to do is every time I refer to this constant, instead of x hat, I'm going to refer to it as x with a chevron, an upside down hat, if you will, just so we don't confuse it with a unit vector. The error vector, for completeness sake, is equal to the b vector minus the projection. So this is the amount that we are incorrect if we're trying to use p as an approximation for b. All right, so I'm going to leave you to look through these examples. He talks about this. He shows us the error vector. He gives us this information, just what I've shown you here. I just wanted to make sure that you understood how he came up with it and make sure that you understand what the dot product is. It's the length of the projection multiplied times the length of the vector we've projected onto, which is why we try to project onto unit vectors, because then of course that length is just 1. Some more information here about the projection. Let me show you one thing, and he does a little bit of the derivation here. He shows the length of p as the length of b cosine. We already talked about that. But let me do a little bit of algebra to show you where the projection matrix comes from. It's not difficult. We're just going to rewrite this. So the p vector is equal to A transpose B divided by A transpose A, all multiplied times the A vector. I can rewrite this because, of course, this piece is just a scalar. So I'm going to put the vector A on the other side, and I have A vector transpose B divided by A vector transpose A. But then I can rewrite this to be A vector times A vector transpose all over A transpose A times B. All I've done is use commutativity. So instead of doing this multiplication first, we're going to do that multiplication first. That's all. Not commutativity, sorry, associativity. So we're just, instead of associating the A transpose with the B, we're going to associate the A with the A transpose. And that is legal for matrix and vector multiplication. So the result of doing this is where the projection vector is equal to, and that is the projection matrix P. So the projection matrix P multiplied times the vector B. So remember, we are projecting B onto A, and the projection vector, the projection matrix, which is doing the projecting, that is equal to, for the one-dimensional case, that is equal to AA transpose, which is an outer product, right? So this is going to be a length of A by length of A matrix divided by A transpose A, which is a dot product. So we have an outer product divided by an inner product, and that's going to be a matrix. And really the A transpose A in the denominator down here, this is just scaling by the magnitude of A squared. Remember, that's equal to the length of the A vector squared. So this is an important relationship because this is the foundation of how we come up with these projection matrices. So continuing on then, we have exactly the derivation that we just discussed to come up with the projection matrix. And he notes here the projection matrix P is m by m for a vector of length m, but it's rank 1 because we're projecting onto this one-dimensional space. And so then he gives us an example. Make sure you walk through this and you understand how to develop a projection matrix. We're going to do our own example. Let me show you what the dot product looks like. And what I have here is just an example of the dot product this is running through and just showing the value of the dot product as we look at the projection of the gray vector onto the line that contains the blue vector. That's how Strang talks about it. It's the projection onto the line, the one-dimensional subspace that contains the blue vector. And what we want to do is we want to just develop the projection matrix that goes with this. So the vector here that we have is 3, 1. Let's take a look at that. And what we'll do is, for practice, we will project the gray vector when it's equal to 0, 3 onto the blue vector, which is 3, 1. So our vector here, I'll shift over to be in blue. Our vector is 3, 1. That's A, and we're interested in projecting onto that. And so we need the projection matrix is equal to A vector times A transpose, and then A transpose A. So the outer product here, this is a 3, 1, and then the transpose is 3, 1, and that's divided by the inner product, which is 3, 1 and 3, 1. So this is going to give us the matrix, which is 9, 3, 3, 1, divided by 10. So our projection matrix is equal to 0.9, 0.3, 0.3, 0.1. So now we can find the projection vector P onto A simply by multiplying by this projection matrix. Don't confuse, of course, projection with permutation. They sound similar perhaps, but obviously they're completely different things. So in this case, we are going to apply our permutation matrix, our projection matrix P, and we said that we're going to take the vector 0, 3, and we're going to figure out what this is. So we have a 0.9 and a 0.3 and a 0.3 and a 0.1 multiplied times 0, 3, and you can see very easily that this is going to be equal to 0.9, 0.3. That is our vector, which for us is the black vector. So let's pull this up, and here it is right here. So this is 0.9 right out to here, and then it's up 0.3. And that's how we calculate that projection. For a projection matrix, we end up doing exactly the same thing. Notice and make sure that you read through this projection onto perpendicular subspaces. That's this I minus P here. Okay. So continue reading through, and we're going to end up looking at projecting onto multiple columns. So the situation, we're not projecting just onto a line, but we're projecting onto subspaces that are defined by more than one vector. So here's the example I want to work with. We're looking at a system, AX equals B, and you know, of course, in order for this to have a solution, the B vector will have to be in the column space of A. An easy check for that is simply to build the augmented matrix and do reduced row echelon form to see whether or not that last equation is 0 equals 1, in which case the system's inconsistent, or if it's just a row of zeros, in which case we have a solution. In this situation, B is not in the column space. And so what we want to do is we want to find the B that is closest to the actual B that we have. Let me show you the picture of what we're trying to do. So here is the column space of A. The column space is defined as the linear combination of the columns, and in this case that linear combination is the cyan plane that you see here. So this is a two-dimensional subspace in R3. The gray vector is the B vector. That's the vector that we want to find a solution for. That's not possible. So what we're going to do is we're going to do the next best thing. We're going to use the projection matrix created by the columns of A in order to find the vector that's closest. So the vector that's closest is this black one here. That's the P vector that we were talking about earlier when we were projecting onto a single vector. And the red vector is the error. So again, in this situation, we are projecting gray onto blue. That projection is the black vector, which now we can solve. Now we can find an X that's going to give us the solution for the black vector. It's not for the B, but it's as close to the B vector as we can get. There are other vectors in the column space of A here, but those vectors are all farther away. The best we can do is to project straight down, perpendicular to the plane. And that's exactly what the projection vector does, or the projection matrix does. And then the error is going to be right here. So let's just do that. Let's build this up. We know that our projection matrix is going to be equal to 4, 0, 1, 0, 2, 1. And we're going to take this outer product, but we're not going to be able to divide by the dot products. So something has to be a little bit different here. And what we're going to do is we're going to utilize this representation down here, which is really saying the same thing. Let me show you. So P is equal to A times A transpose A inverse A transpose. That's the projection matrix. Remember, what we were using was P is equal to A vector transpose divided by A transpose A. But that's really the same as the A vector multiplied times 1 over A transpose A, which is just a scalar, times A vector transpose. And you can see the similarities here with the A and the A transpose on the outside, and then in the middle we have this scaling. And that's exactly what this does, where the inverse, of course, gives us the 1 over, if you will. That's the reciprocal in matrix terms. So what we need to do is to create this calculation. So let's go ahead and do that. So I've pulled up a live script here in MATLAB, and now we're just going to build. First, we're going to build A transpose A, which of course is A transpose times A. And then we're going to take the projection matrix is equal to A times the inverse of A transpose A multiplied times A transpose. And let's run this and see what we end up with. So we start out with our matrix here. Here's A transpose A, and then the resulting projection matrix is right here. So you notice a couple of things. It's symmetric, right? And that's not a surprise because A transpose A is going to be symmetric regardless of the dimensions of A. And then really on the outside, we have A times A transpose, which is also symmetric. The idea of what's happening here is exactly the same as what we discussed here. It's really A times A transpose with this scaling in the middle, just exactly like we have here. It's just the fact that we don't have dot products. So what we're going to do then is we're going to project our negative 5, 1, 4 vector and see where that ends up. So we're going to take P and we're going to multiply it times B. B was equal to negative 5, 1, 4. And P times B, this is what Strang calls the projection vector, little p. So it's a little bit difficult sometimes to see this in MATLAB, but this is the idea. So we will recreate, and here is the closest vector we have in the column space to the vector that we want to try to solve for. This is the least squares problem. We'll be talking about this a lot more next time. I just want you to understand from the picture what's happening. The vector, the black vector down here is this one right here. And then the error is going to be orthogonal. That's equal to, we can calculate the error vector. The error vector is going to be equal to b minus the p vector. So running this, we have an error vector that looks like this one here. And the length of that vector is minimized. It's very easy geometrically, and he explains this in the section. It's very easy to see that the closest we could get would be the situation where the error vector has minimum magnitude. Any other approximation for b that's in the column space will have a longer error vector and will not be as good of an approximation. So what we're trying to do is minimize the length of the error vector to give us the best possible approximation for b in the column space of A. So let's finish this up. There's one more idea that we want to make sure that we have down, and it has to do with our 4 fundamental subspaces over here. So this conversation, you want to read through this. This is where he derives what's called the normal equations. So these equations here are called the normal equations because literally they are normal. They are the places where the columns, which are the rows of A transpose, the columns of A are orthogonal to the error vector, which is right here. So the error vector is equal to b minus p, but that's equal to b minus, and the p vector is this ax, which gives us the approximation for the length of the A that we want. So this is giving us the X chevron, if you will, is giving us the linear combinations of the A matrix that generates the P vector. So these are the normal equations. I'm going to leave you to read through this conversation. And what I want to do right now is just emphasize this conversation here about what it is that we are attempting to do. So we have the problem ax equals b, but b lies outside of the column space. Recalling this is the column space of A, this is the null space of A transpose. So our b vector, similar to the conversation we had last time, has 2 components. It has a component in the column space and it has a component in the null space. And what we're trying to do then, so this piece here is really the p vector. The projection of b into the column space is the projection vector, which means the vector here is the error vector. The piece of b that lies in the null space of A transpose, that's the error. So what we're going to do is we're going to take the problem and we're going to, because we can't solve this, we're going to solve for ax equals p. We want to project b into p, and the question is, how do we come up with this problem? And that's the discussion associated with the normal equations and how we're really just forcing A transpose times the error vector to be equal to 0. Well, we already know that that's the case. We know that the E vector is in the null space of A transpose. So we're using that fact to generate an equation. And that equation is A transpose times the E vector is equal to 0. And this fact is what we're using to try to set up and solve the problem. I'll leave you to read through all of this. There's a little bit of information in here. I want to make just a few highlights, and then we'll get into the questions. So, warning, it looks like this is deceptive. It looks like we might be able to try to split up A transpose A inverse into A inverse times A transpose inverse. And he goes through a little discussion as to why that's not going to work. Okay. Now, he makes this note here about A transpose A is invertible if and only if A has linearly independent columns. For the situation of least squares, which is where we're going to be using this next lesson, we're going to have linearly independent columns because we get to choose what the A matrix is actually going to be. We're going to choose the subspace that we're going to project the problem onto to try to solve it. And a little bit more information then that he provides. Obviously, you don't have to know the proofs, but he does provide a nice summary of the important pieces of this projection matrix idea. Let's talk about the problems. So these are the problems that we're going to have for today. Starting out then, what I want you to do is find a projection matrix. So this is just projecting onto this subspace. Once you find the projection matrix, take some vectors. Take a vector that's in the span and see what its projection is. And then take a vector or two that's not in the span and see what the projection is. You can plot them if you want to. Here's a matrix, and notice that the last two columns of this matrix are the same as these two vectors here. And the question is, what is the projection of this vector onto the column space of A? So we want to find the projection matrix onto the column space of A. And then the question is, what is the error vector for our projection? And then finally, you have a Sanderson video for today's lesson, which is video number 9, dot products and duality. And in that video, Sanderson talks about projections. He talks about the dot product and how it is interpreted as projections. And so you can address this question using that video. Thanks, and we'll see you in class.